Okay, in many of the problems we use a very general equation to calculate acceleration or force. What's that? Newton's second law. Okay, don't forget. Whenever you find that you don't think that you have any equation, think about Newton's second law. That's our most general equation. So what can we do is that if we can somehow, as any standard problem, figure out what is the net force acted on the satellite. And in this case, the acceleration here you calculated should be the centripetal acceleration. And then from this, you can calculate the velocity. So basically, we're going to calculate force, acceleration, and then v, right? Now, to calculate, but there is a question, okay? Okay. Let's first look at the force acted on the satellite. What is the force acted on the satellite? Okay, for satellite, how many forces acted on? What is that? Okay, the gravitational force Fg. There is no any other force acted on the satellite, right? If you ignore the air resistance. Okay, because it's basically hanging in the space, so there's no any other contact force. The only force is Fg. So from Fg, because it's in the circular motion, okay, so this is the Earth, this is the satellite. The Fg is in this direction, it's in the centripetal direction, right? So this Fg is to provide the centripetal acceleration. So from this equation, we should be able to calculate the centripetal acceleration and then calculate the velocity for the circular motion. Okay. Any questions here? And now, one of the questions I would like to ask is that it seems that to calculate A sub c, we need to know the gravitational force and we need to know the mass of the satellite. Okay. But I didn't give you the mass of the satellite. Can you guess what happened? Or is it a wrong problem? Okay, any idea why I don't even give you the mass of the satellite? Mass of the satellite is 0? No, mass of the satellite. It cannot be 0. If you have 0, then you wouldn't get any quantity. 0 multiplied by any quantity gives you 0. So, usually, okay, when you write down equation and you find that, okay, I need this quantity, and you cannot find it in the problem, you need to expect it may be cancelled during the calculation. Okay. Now let's see if it's cancelled. The gravitational force equals to G multiplied by, if this is the mass of the Earth and the mass of the satellite, right? Divided by r squared. R is the radius or the distance between the satellite and the center of the Earth. Okay. Equals to MAC. So it cancels. Right? So you don't really need the mass of the satellite. And you need the mass of the Earth, okay, it's a constant, okay. And G is universal constant, so you should be able to find the value for both of them. But now the question is, what is the radius here? Okay, please note, yes, that's it. And please, but you need to think this more carefully. Precisely speaking, this radius should be this, right? From the center to the center. But if the satellite is near the Earth's surface, so this height is actually very small compared with the Earth's radius. Okay. So in that case, R is almost the same as RE, the radius of the Earth. Okay. So, but this is only true when we were talking about some satellite near the Earth's surface. Okay. In fact, many of the satellites satisfy this requirement. But if you have some satellites is very far away from the Earth, okay, if you are launching something to the moon, so this radius r is of course not the same as r in English. Okay, so just be sure why we can write it as r in this case. So we get GME divided by RE squared equals to AC. Okay. And then you can already calculate the number for AC here, but it's better just leave it like that and do the calculation later. So AC, on the other hand, equals to V squared over R. Okay. In this case, equals to V squared over RE, the radius. So GME over RE squared equals to V squared over RE. Okay, so one of the RE here cancels. You get V squared equals to GME over R. So V equals to square root of. So with this quantity, you can calculate it. Okay, you can do the calculation by yourself, and you will see that this should be the quantity we give you. Okay, so 7.9, sorry, not meter. Okay, so it will be 7.9 times 10 to the power of 3 meters per second. Any question here? Okay, so again here, for this kind of problem, the most important thing is to identify that the key is the centripetal acceleration in this case is provided by the gravitational force. Okay, that's our key equation here. Okay, and for the escape velocity, so far we don't have a way to calculate it. We have to calculate this kind of the escape velocity. We have to learn how to use the energy conservation law later. Now, I would like to talk about the interesting phenomenon related to what we have learned here. So, if you want to make something to escape from the gravitational force or gravitational field of some heavenly body, say Earth, okay. So you have to make the velocity larger than the escape velocity of the Earth. Okay. If you want to make it, it can go to infinity. And different heavenly body may have different escape velocity. Okay. Like for the Earth, is 11.2 kilometer per second. For the moon is 2.4. For the sun is 617.5. Okay. Usually it depends on the two factors. So one is the mass of the star or the planet. Another is the radius of the heavenly body. The larger the mass, the larger the required velocity. And the smaller the radius, the larger the required velocity. Okay. So But it's possible for some star, the escape velocity even larger than that. If V escape is larger than the speed of the light. So in that case, even the light cannot escape from the star. So the star becomes dark or blank. That means you cannot see the light emit from the star. And that's called the black hole. Okay, so that's the original idea about why in the universe we expect there is black hole. And experimentally, how can we discover black hole? Because you cannot see it. How can we try to study the black hole? Okay, but we can observe black hole indirectly. It happens sometimes. If black hole is in a double star system, okay, so if there is a big star and there is a black hole here, because black hole has a huge gravitational force, it may attract the gas from the accompanying star. Okay, so the gas will pour into the black hole. Okay, and during this process, these gases will be accelerated to very high speed, so it emits X-ray. Okay, so it will emit X-ray, and we can try to observe it and determine if it's a possible black hole here. Okay, so this is what we are doing to study the black hole. By this way, we identify several black holes, okay, in the space. But of course, if you don't have the star, then you really don't have any way to observe it. Okay. In fact, this not any way. This is just one way to observe it. Another way is that it's even more fun, interesting. That okay, black hole. If the black hole is in front of the star, okay, then due to the huge gravitational force for the black hole, this will happen. Okay, the light emitted from the star, okay, naively thinking it will be blocked by the black hole, so we cannot see it. But in fact, what happens is that for the black hole, because the gravitational force is so huge, so it can burn the light. Okay, so the light will not go through a straight line. So it will go like this. And then we can observe, so it will form some, so what you are going to see from this direction, you may see like several identical stars around the black hole. Okay, probably a ring, okay, around the black hole. So in this case, happens is called the gravitational lens to bend the light, and it also suggests us, okay, in between the star and us, there is a black hole here. But to understand these things, it requires study of general relativity. Okay. So that's how we identify the black hole. But to understand what is black hole, it's just some classical mechanics we discovered here. It's about the escape velocity. And so this is black hole, and by the way, you can skip this.